All right, we are back. And to recap, the problems we've solved and the problems we've created, our arrays were problematic because they were a fixed size, and that can get us into trouble, or it causes us to waste more space preemptively, even though we might not ever use it. So we introduced linked lists again to solve that problem by being more dynamic and only allocate as much memory as we need on demand, step by step. But of course, we're spending extra space for the pointers. We might gain performance if we at least prepend all of our elements to it, but we lose time again if we append or insert in sorted order. So it's not clear, frankly, I think to me, in even hearing these upsides and downsides, if there's a clear win. But maybe there's a way to get the best of both worlds by trying to capture the upsides of having information that is kept in sorted order, that allows us to maybe divide and conquer still, but still gives us the dynamism to grow or shrink the data structure. And thus were born trees. So what we're about to explore are variants of these ideas of arrays and linked lists, and see if we can maybe kind of mash up some of those building blocks and create more interesting, more compelling solutions that are even not just one-dimensional, sort of left to right, but are maybe two-dimensional and sort of have different axes to them or dimensions. So a tree in the real world, of course, tends to grow up from the ground like this, but it tends to branch out, and branches branch. And that might already in your mind's eye evoke notions of forks in the road or conditionals, as we've seen. And let me propose that we first consider what the world calls binary search trees. And so bi is back in that we can do things in half and half and half somehow if maybe we think about arrays a little bit more cleverly. So here's an array of size 7. And I chose that deliberately because there's a perfect middle, there's a middle of middle, and so forth, just like the lockers a few weeks back. So when the world of arrays, like this was actually pretty efficient because we can do binary search and middle of middle, middle of middle of middle, and so forth. And that gave us logarithmic running time. But it's only size 7, and we concluded that it's going to be like big O of n headache to copy this into a slightly bigger array, free the old memory, and so forth, and thus were born linked lists. But with linked lists, we lost log of n running time. Why? Because we have to always start at the beginning to get, for instance, to the middle or to the end of the list in the worst case. But what if we start to think a little more cleverly in multiple dimensions? So just for the sake of discussion, let me highlight the middle of this here array. Let me highlight the middle of the middle, and then the middle of the middle of the middle. So there's sort of implicit structure here. There's a pattern of sorts. And in fact, just to make this more obvious, let me not treat this in as one dimension, left to right, but how about 2, and give myself a bit of vertical space. So it's the exact same array, but allow me to just think about it now as though the middle element's way up here, the middle of the middles are slightly lower, and the middle of the middle of the middles, or the leaves really, are at the bottom of this tree. And that word's deliberate. We actually borrow vernacular from the world of trees where the leaf nodes, or leaves, are the ones at the very bottom, and the root node is the one at the very top. So for the sake of discussion, computer scientists draw trees like this instead of like this, but it's the exact same idea. They just tend to grow down in discussions. More like a family tree if you drew those growing up, for instance. So what's interesting here? Well, at the moment, we've sort of broken the array model because this memory is absolutely not contiguous because this number's here, this number's here, 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 and here. It's all over the place. But we do have pointers now in our toolkit, whereby even if these numbers are anywhere in the computer's memory, we can kind of stitch them together like we did string and those balloons. Now, it's not sufficient just to have one piece of string for each node or one pointer, but what if we actually give each of these nodes not just a number, like the number 4, the number 2, the number 6, let's give them each a number and 2 pointers, a so-called left child and a right child, so to speak. So we could do this. And I'm going to abstract away now. Technically, they're not even rectangles anymore. Like they're really long rectangles, or they're like sort of upside down T's that have 3 boxes to them. But I'm just going to abstract away nodes now as just simple squares. And it's an implementation detail as to what the structs actually are. But the arrows suggest that each of these nodes now has 2 pointers. You don't have to use them. The leaf nodes have nothing to point to, so those can all be null probably. But each of these nodes now has 2 pointers. Now, what's the implication of this? This here is what we call a binary search tree, because one, and first and foremost, it's obviously a tree, but it also is a data structure that's kept in sorted order, whereby notice what is true. If you pick any node in this tree, like the number 4, everything to the left of it, its left subtree, so to speak, is smaller. Everything to the right of it, its right subtree, is larger. And that's true elsewhere. Look at the 6. Everything to the left is smaller. Everything to the right is bigger. And same thing over here. So in some sense, this is a recursive data structure because you can say the same thing about each of these nodes because each of these subtrees compose a larger tree. Or conversely, this big tree is a composition of 1, 2 subtrees plus one more node. So think back to our Mario example in those bricks. Well, what's a pyramid of height 4? Well, it's just a pyramid of height 3 plus one more row. What's a tree of height 3? Well, it's 2 subtrees of height 2 plus one more row, or really one new root node to connect them. So this already is sort of a recursive data structure by that logic. How do we translate this into code? Well, we won't sludge through so much low-level C code this time around, but let me propose that we could implement a node now as being similar in spirit to what we did last time, where every node used to have a number and a next pointer. But now let's actually make some room for ourselves and redefine a node as still having a number, but now having two pointers. And I'll call them obviously left and right, though we could call them anything we want. I could call it next and previous, but really left and right would seem to make more sense with children of a given node like this. So this in C is how we might implement, therefore, a node in a binary search tree. And so let's consider pictorially what the running time is of searching for something. If this here is the tree, and it follows that binary search tree definition where everything to the left is smaller, everything to the right is bigger, well, how many steps might it take if you have n nodes in a tree like this? Well, it's not going to take me n steps because I certainly don't have to look through every node. And in fact, just like a linked list starts on the left-hand side, so to speak, though that's just an artist's rendition, just as a linked list starts on one end and you have to traverse the whole thing, a tree, because it's two-dimensional, always starts in memory at the root node. So this is always where you start any operation: insertion, deletion, searching. So by that logic, in the worst case, if there's n nodes here, how many steps would it seem to take? It's not big O of n, but so it's actually back to big O of log n. Why? Because actually, if you kind of think of the height, there's roughly 8 nodes in here, and log base 2 of 8 is actually 3. And so 1, 2, 3 is the height of this tree. So in the worst case at the moment, it seems that it's only going to take me like 1 node, 2 nodes, 3 nodes, or really just 2 steps to get to the very bottom of this tree to decide, is a number there or not. I certainly can ignore like this entire subtree. Why? Because I'm searching for the number 7, just like the phone book from week 0. I can kind of divide and conquer this problem. If I'm looking for 7, I don't need to bother wasting any time looking at this entire subtree, which is almost 50% of the picture on the screen. And so I can focus on this half, then this half, and boom, I'm done. So we sort of have binary search back. We have the metaphor of the lockers back by operating now in 2 dimensions to mitigate the reality that our memory is no longer contiguous, but that's fine. We can follow these arrows. We can use these pointers instead to get anywhere that we actually want. So any questions now on trees, or specifically binary search trees, which I dare say are sort of like the best of both worlds? All of the upsides of an array, and it's like log n running time, and all of the upsides of the dynamism of linked lists, because this thing can grow and shrink and doesn't need to be contiguous. Any questions on this? All right, well, the code too lends itself to relative simplicity. And here's where recursion applies not just to the structure of the data, but also the code itself. So just for the sake of discussion, we won't run this kind of code. We'll just look at it on screen here. Suppose you're implementing a function called search, whose purpose in life is to search a tree and return true or false. I found the number you're looking for. Well, here's the number I'm looking for. It's one of the arguments. And the first argument, more importantly, is actually a pointer to the tree itself, a pointer to the root of the tree. And that's all the information we need to search a tree and go left, go right, go left, go right. How? Well, let me do this. As always, we'll have a base case when it comes to recursion, because if there's no tree there, then it makes no sense to even ask me this question. I'm just going to return false. If you hand me null, there's nothing to do, return false. But suppose that you don't hand me null, and suppose that the number I'm looking for is less than the number in the tree at the moment, the number at that root. Well, what do I want to do? I effectively want to go left. I want to search the left subtree. How do I do that? I'm going to return the recursive return value from the same search function, passing in a slightly smaller tree, a so-called subtree, but the same number. And this is where recursion is kind of beautiful. Like, look at the relative simplicity of this. If search exists, which it doesn't exist in its entirety yet, but we'll get there. If you want to search half of the tree, just go there. So go to the root of the tree, follow the left child pointer, and pass that in, because it's a tree. It's just a smaller tree, but pass in the same number. What if, though, it's a bigger number? So what if the number you're looking for is bigger than the number at the root of the tree? Well, then just search the right subtree instead. And now logically, what's the fourth and final case? If it's equal, so I can express that as if the number you're looking for equals the number in the tree, that is the root of the tree, then I'm going to go ahead and return true. And you might remember from our days with Scratch, like even this conditional is not necessary. I just did it to be explicit. We can tighten that up as just an else instead. And that's it. And this is where, again, recursion finally is maybe a little more accessible, a little more obvious in its cleanliness. There's relatively little logic here, but what's important is that these recursive calls here and here are dividing and conquering the problem implicitly. Why? Because it's solving the same problem, search for a number, but it's doing it on just half of the tree, or the other half of the tree. And because we have this base case here, even if you get all the way to the bottom of the tree and you try to go down the left child, or you try to go down the right child, but those pointers are null, then you know you didn't find it, because you would have returned true sooner if anything had been, in fact, equal. So that then is recursive code for searching a binary search tree, which is, again, just to connect the dots of what we introduced last time of actually doing things now recursively and revisiting some of our own week 0 problems. But I'm kind of lying to you here. Like, yes, this is a binary search tree, but it's not always as pretty as this. It's certainly not always 7 elements, but it doesn't actually have to be as well balanced as this one here is. In fact, suppose that we insert the following numbers into an empty list, starting with 2. I can plop the 2 right there. That's the current root of this tree. Suppose, though, that I insert next the number, how about 1? Well, it stands to reason that it should go now to the left. And so now this is the tree of size 2. Now I insert the number, say, 3. It, of course, can go there. So that makes perfect sense. And I just kind of got lucky. Because I inserted these numbers as 2, then 1, then 3, I very cleanly got a balanced tree that's sort of, weighted properly left and right. But what if you have a more perverse set of inputs, so to speak? You're not lucky, and like the worst possible situation happens in terms of the order in which the human is inputting data into this data structure. What if the human inserts 1 first? OK, well, it goes as the root of the tree. But here's where things start to devolve. What if the human then inserts 2? OK, it goes there. What if the human then inserts 3? Well, according to our definition, it goes there. It looks like part of a tree because of how I've drawn it, but what is it really? If you kind of tilt your head, right? It looks really just like a linked list. And there really is no second dimension. I've drawn it this way, but this, for all intents and purposes, is a linked list of size 3. Why? Because there's no having. There's no actual choosing left or right. Now, this is fixable. How could you fix this? It's still the same numbers, 1, 2, 3, and it does adhere to the binary search tree definition. Every number to the right is greater. Every number to the right is greater. Every number to the left is, well, it's inapplicable, but it certainly doesn't violate that definition. Could you kind of fix this tree somehow and make it balanced so it's not devolving into big O of n, but is still technically log of n? What should be the root? So I could reverse the pointer from 1 to 2, yeah. And so sort of pictorially, if I kind of take this and I just kind of like swing everything over and make 2 the new root, then indeed, this could be the new root up here. 1 could be hanging off of it over here, and 3 can be hanging off of the 2 as is. So long story short, when it comes to binary search trees, by themselves, they don't necessarily guarantee any sort of balance. So even though theoretically, yes, it's big O of log n, which is fantastic, not if you get a perverse set of inputs that just happen to be, for instance, the worst possible scenario. Now, it is fixable. And in fact, in higher level courses in computer science, specifically on algorithms and data structures, you'll be introduced, if you go down that road, of how you can tweak the code for insertion and deletion in a binary search tree to kind of make these fixes along the way. And it's going to cost you a few more steps to kind of fix things when they get out of whack. But if you do it every insertion or every deletion, at least you can maintain a balanced tree. And you'll learn about different types of balanced trees. But for our purposes now, we don't necessarily get that property, even if we do want log n, unless you keep it balanced along the way. Now, what about other combinations of arrays and linked lists? It's like we can really start to mash these things up and see what comes out of them. Dictionaries are another abstract data type, similar in spirit to stacks and queues, in that you can implement them in different ways. A dictionary is a data structure that stores keys and values. And those are technical terms, keys and values. The analog in the human world it would be like literally a dictionary that you'd have in a classroom, like a dictionary with words and definitions, more generally known as keys and values. So that's all a dictionary it is. It associates keys with values. So for instance, you could think of it almost as like two columns in a spreadsheet, where on the left you put the key, on the right you put the value. Or specifically, you put the word in a dictionary and the definition thereafter. And that's roughly how the pages, on the printed pages in a dictionary, are laid out. So dictionaries associate words with definitions, or more generally, keys with values. But it's an abstract data type in that we could implement this in a bunch of ways. We could use maybe two arrays, one array for the keys, one array for the definitions. And you just kind of hope that they line up. Bracket I in this one is the maps to bracket I in this one. But an array is not going to give us the dynamism that we want, right? You might run out of space when Merriam-Webster or whoever comes up with, adds new words to the English language. You might not want to be using an array. You might want to use a linked list. But again, linked lists kind of then devolve into big O of N, and that's not good for dictionaries and spell checking. If you have to check every possible word to find something, getting something that's a little faster than that is compelling. So let's consider how maybe Apple, maybe Google, maybe others are actually implementing contacts, because even though I implied in week 0, and maybe outright said, it's an array. It's a big list of all of your names of contacts, maybe of some fixed size. They probably better be using some variant of a linked list. Otherwise, you could never add more friends, potentially. You'd max out, and they'd say you have to unfriend someone just to fit it. As an aside, this is sort of true in the social media world. Like once you have like 5,000 friends on Facebook, you can't have 5,001. Once you have some number on LinkedIn, you can't have more connections. That's not necessarily that they're using arrays, but it is the same implication that they've chosen some finite size for memory. So how might we consider implementing a dictionary specifically for your address book or your contacts, so you can store the names of everyone, ideally alphabetically, but also their phone numbers and maybe anything else? Well, ultimately, we want to be able to get at someone's name and lead to their number. So the keys and values for our discussion here will be names are the keys and phone numbers are the values. But the values themselves could also include email address and mailing address and all of that. But we'll keep it simple: names and phone numbers. So here's how you might think about this, or draw it on a chalkboard, 2 columns, or in a spreadsheet, left and right. But how could we actually implement this in memory? Because ideally, we don't want it to devolve into something linear. Like we don't want to have to look through all of my friends and family and colleagues to find someone whose name starts with Z, for instance, or anything else. It would be nice to have something logarithmic with binary search. But with binary search, again, we have to maybe use a tree instead, but now we have to use 2 pointers instead of 1. Like there's a lot of trade-offs here. But let's see how else we could solve this same problem. Because wouldn't it be nice, and we've not really talked about this before, if we instead aspired to this sort of holy grail of algorithms? Like the best algorithm out there is surely one that's big O of 1, like constant time. Because what that means is that it doesn't matter if you have 1 friend, 10 friends, 100, 1,000, a million, a billion friends. It doesn't matter how big N is, your searches will always take you the same amount of time. It is independent of N. And that's why it's sort of the ultimate goal for performance. So can we get to this aspiration? Well, a couple of building blocks. There's this notion in computing known as hashing. And hashing is a technique, literally a function in math or in code, that actually takes any number of inputs and maps them to a finite number of outputs. So if you think back to like high school math, domains and ranges, you can take an infinite domain with any values in the world, but it reduces them, a hash function, to a finite range of specific values. So for instance, it's no accident that we have these 4 buckets on the stage now, each of which has a suit from a deck of cards. We got, for visibility's sake, the biggest cards we can. These are the super jumbo playing cards. And in this box are a bunch of randomly ordered playing cards. And typically, if you were to ever like play some game, or you wanted to sort these for some reason, how would you go about sorting them by suit and also by number? Odds are, if you're like me, you'd probably kind of take some shortcuts and maybe pull out all of the hearts, pull out all of the spades, pull out all of the clubs, or you'd kind of bucketize it into categories. And that term is actually actually technical. Here are 4 buckets to make this clear. And for instance, if the first card I find is like the 5 of hearts, you know what, just to kind of make my life easier, I'm going to put that into the hearts bucket. Or here we have 4. Here we have 5. Here we have 6. Here we have queen. And notice that I'm putting these cards into the appropriate buckets. Why? Because ultimately, then I'm going to have 4 problems, but of smaller size. A 13 size problem, 13, 13, 13. And frankly, it's just going to be easier cognitively, dare say algorithmically, to then sort each of the 13 cards in these buckets rather than deal with like 4 suits somehow combined all together. So if you've ever in life made piles, if you've ever literally used buckets like this, you are hashing. I'm taking some number of inputs, 52 in this case, and I'm mapping it to a finite number of outputs, 4 in this case. So hashing, again, just takes in inputs and hashes them to output values in this way. So beyond that terminology, let's consider what we can now do with hash functions that's a little more germane to storing things like our friends and family. And colleagues in dictionaries, a hash function is just one that does that. I, as the human, was just implementing or behaving like a hash function. But technically, a hash function is actually a math function or a function in C or Scratch or soon Python or other languages that takes as input some value, be it a physical card or a name or a number or something else, and outputs some value. And we can use hashing as an operation to implement what we'll call hash tables. And that's kind of what that dictionary was. If you think about how I drew it on the screen as 2 columns, it's like a table of information. Keys on the left, values on the right. So what is a hash table? The simplest way to think about it is that this is an amalgam of, a combination of arrays and linked lists. Right? We kind of borrowed some ideas of linked lists a moment ago to give us trees in 2 dimensions. What if we stick with this idea of having 2-dimensional world, but now use an array initially, so we get the speed benefits of arrays, because everything's contiguous. We can do simple arithmetic and jump to the middle, or the middle, or the middle, or the first, or the last very easily. And then, you know what, let's kind of use the horizontal part of the screen to give us linked lists as needed. So for instance, if the goal at hand is to implement the contacts in my cell phone or my Mac or PC, let me propose that we start, at least in English, with an array of size 26. Of course, it's 0 index, so it's really location 0 through 25. And for the sake of discussion, let me propose that location 0 represents A, location 25 represents Z, and then everything else in between. Why? We know from C that we can convert, thanks to ASCII and Unicode, from letters to numbers and back and forth. So in constant time, we can find location A. In constant time, we can find location Z. Why? Because we're using an array, just like in week 2. All right, well, suppose that I want to think about these more as letters of the alphabet, the English alphabet, rather than numbers, so it's equivalent to label them A through Z. And suppose now I want to start adding friends and family and contacts to my address book. How might this look? Well, if the first one I want to add is Mario, Mario's name starts with an M, and so that's, A, B, C, D, E, F, G. OK, M goes there. So I'm going to put Mario at that location in the array. After that, I add a second person. For instance, how about Luigi? Well, L comes just before M, so it stands to reason that it goes there in the array. Meanwhile, if I go and add another character like Peach, she's going to go there, a few spots away, because her name starts with P. Meanwhile, here's a whole bunch of other Nintendo characters that happen to have unique letters of their first names, and there's room for everyone. Room for everyone on the board, A through Z, with some blanks in the middle. But you can perhaps see where this is going. When and where might a problem arise with this array-based approach? Yeah, so when we add someone else whose name collides with one of these existing characters just because by accident they have a name that starts with the same letter. So for instance, there's Lakitu here, who collides with Luigi potentially. Here's Link, who collides with both of them. But I've drawn a solution to this along the way. I could, if I was Draconian, just remove Luigi from the data structure and put Lakitu in, or remove and then put Link in there instead, but that's kind of stupid if you can only have like one friend whose name starts with L. Like, that's just bad design. But what if we now, in the off chance I have two friends whose names start with the same letter, well, I'll just kind of string them together, link them together, no pun intended, using pointers of sorts. So my vertical here is an array, and this is just an artist's rendition. There's no actual notion of up, down, left, right in the computer's memory, but this is my array, always of size 26. And each of the elements in this array are now not a simple number, but it's a pointer to a linked list. And if there's nothing there, it's just null, 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 null. But otherwise, it's a valid address that points to the first node. And you know what? If we have multiple names with the same letters, we can just string these nodes together using pointers as well. So a hash table then, as implemented here, is an array of linked lists. And that allows us to, one, get some speed benefit, because look how fast we inserted or found Mario, Luigi, and Peach. But it still covers the scenario where, OK, some people can have the same first letters. Some of these names will collide. So collisions are an expected problem with a hash table whereby two values from some domain happen to map to the same value. And frankly, you'll see this here too. So these buckets are technically a finite size. They're definitely big enough for 13 cards each. But you could imagine a world where if I'm using 2 decks, 3 decks, or 4 decks, I'm going to run out of space, and then my data structure can't fit any more information. But we're not going to have this problem here, because the linked lists, as we've seen, can grow and even shrink as much as they want. In the world of Nintendo, there's actually lots of collisions, and these aren't even all of the characters. So that's then a hash table. So with a hash table in mind, how fast is it? Did we achieve that holy grail of like constant time? Well, for some of these names, if I back up, yeah, it's kind of constant time. Like Yoshi and Zelda, boom, constant time. Location 24, location 25. Some of them, though, like Luigi, Lakitu, Link, it's not quite constant time, because I first have to get to Luigi's location, and then I have to follow this linked list. So technically then, what's the running time of searching a hash table? Sometimes you'll get lucky, but sometimes you won't. Consider the worst case. Big O is often used to describe worst case. So what would be the worst case in your own context? A little letter? So N, why? Correct. And so to summarize, like, some weird scenario, like all of your friends and family and contacts could have names that start with the same letter. And then it doesn't matter that this is a hash table with an array of linked lists. For all intents and purposes, if your friends' names only start with the same letter, all you have is a linked list. Much like with a tree, if you don't keep it balanced, all you have really is a linked list. So technically speaking, yes, hash tables are big O of n, even if you're good about, even if you have friends, in the worst case, hash tables are big O of n. Why? Because it can devolve into this perverse scenario where you just have lots and lots of collisions, all at the same values. But there's got to be a way to fix this, right? Like, how could we chip away at the length of these chains, so to speak? Could I decrease the length of these linked lists so that with much higher probability there's no collisions? Well, maybe the problem is that I started with just 26 buckets. 4 buckets here, 26 here. Maybe the problem is the size of my array. So what if I instead just give myself a bigger array? And it's too big to fit on the screen. But what if I instead have a bucket for names that start with LAA and LAB and LAC, LAD, dot, 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 all the way down? Now, when I hash these names into my hash table, Lakitu is going to end up at their own location here, Link at their own location here, Luigi at their own location here. And so now I don't have linked lists. I really just have an array of names. So now I'm actually back to constant time. Why? Because so long as every letter of the alphabet has an ASCII value, I can get that in constant time. And we did that as far back as week 1. And so I can figure out what the arithmetic location is of each of these buckets just by looking at 1, 2, 3 characters, or the total number of letters that I care about, which is just 3 in this case. So this feels like a solution. Even though I haven't drawn all the names, it feels like we've solved the problem. But what's the downside or trade-off of what we've just done? Sorry? Memory. So not pictured here is the dot, 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 and everything above and everything below. This just exploded in terms of the number of locations in this array. Why? Because if I'm taking into account not just the first letter, but the first, the second, and third, that's 26 to the third power. 26 times 26 times 26. And even though there's going to be a crazy number of names that just don't exist, I can't think of a Nintendo character whose name starts with LAA, you still need that bucket. Why? Because otherwise you don't have contiguousness. You can't just arbitrarily label these buckets if you want to be able to use a function that looks at first, second, third letter and then arithmetically figures out where to go, whether it's 0 to 25 or 0 to 26 to the third power minus 1 being the number of buckets there. So there's a trade-off there. You're wasting a huge amount of memory just to give yourself that time. But that would then give us constant time. So in that sense, if we have an ideal hash function whereby the function ensures that no values collide, we do actually obtain that holy grail of big O of 1, because it only takes 1 or maybe 3 steps to find that name's location. Now, to make this clear, how do we translate this to something like code? Well, here again is the struct we used last time for that of a person, and a person had a name and a number. Here, for a hash table, we might do something a little bit differently. We might now have a node in a hash table store something a little of a person, and a person had a name and a number. Here, for a hash table, we might do something a little bit differently. We might now have a node in a hash table storing the person's name, person's phone number, and a pointer to the next such person in that chain if needed. Hopefully this is going to be null most of the time, all of the time, but we need it just in case we do have that collision. We've seen in our pictures the names, like Mario, Luigi, and so forth. We didn't see the numbers, but that's what's inside of those boxes on the picture. But that kind of node would give us what we need to build up these linked lists. Meanwhile, what is the hash table itself, that vertical strip along the left? Well, it's really just a variable, we could call it table for short, of size 26. And each of the locations in that array that was on the side here, at least in the simple, small version, was a pointer to a node. So it's null if there's no one there, or it's a valid address of the first node in the linked list. So this then is a hash table, and each of those nodes, to be clear, would be defined as follows. So what's the takeaway then with a hash table? Ideally, with a good hash function and with a good set of inputs, where you're not presented with some perverse set of inputs that's like all of the friends whose names start with the same letter, ideally, what the hash function will be doing for you is this. The input is going to be someone's name. The algorithm in the middle is going to be the hash function. And the output is the so-called hash value, or location in this case. So for instance, in the case of Mario, when we had just 26 buckets total, the input to the hash function would be Mario. That hash function would really just look at the first letter, M in that case, and would ideally output the number 12. I did the same thing, but in my head, whenever I pulled out a card like the 5 of diamonds here, I figured out, OK, that's location 0 out of my 0, 1, 2, 3, or 4 total buckets. Here, we're doing it instead alphabetically, and so someone like Luigi, meanwhile, would have a hash value of 11. These numbers would be bigger, of course, though, if we're looking at 1, 2, 3 letters instead of just 1. So with that said, if we were to implement this in actual code, a hash function, I did it sort of physically by acting out the cards. Here is how we might implement this in code using C. I could have a function called hash, whose argument is a string, aka char star, a name of which is word, where the word is like the first word in their name. We want this function to return an int, which ideally in this case of 26 buckets would be a number from 0 to 26. And how do we achieve that? Well, if we use our old friend ctype, which had a function like toUpper from a couple of weeks back, we could pass in the first letter of that word, capitalize it, which is going to give us a number that's 65, 66, 67 on up for the 26 English letters. And if I subtract 65, aka quote unquote a, single quotes because it's a char, that's going to mathematically give me a number between 0 and 25 inclusive. There's a potential bug if I pass in punctuation or anything that's not alphabetical, like bad things will happen, so I should probably have some more error checking. But this is the simplest way in code that I could implement a hash function that looks only at the first letter of their name. Probably not ideal, because I can think of friends in the real world who have the same first letter of their name. Whether this is better or worse than looking at 2 letters, 3 letters, 4 letters, it's going to depend on how much memory you want to spend and how much time you want to ultimately save. Let me tweak this, though, a little bit. It's conventional in C, just so you know, that if you're passing in a string, that is a char star, to a function, and you have no intention of letting that function change the string, you should probably declare the argument to the function as const. And that will tell the compiler to please don't let the human programmer actually change that actual word in this function. It's just not their place to do so. And we can actually do something else. In a hash function, because you're using, in this case, the output, the integer, as a location in an array, it had better not be negative, right? You want it to be 0 or positive. And so technically, if you want to impose that in code, you can specify that the int that's being returned has to be unsigned. That is, it's 0 on up through the positive numbers. It is not a negative value. So this is slightly better than the previous version where we didn't have these defenses in place. All right, so what does this actually mean? In practice, you don't get to necessarily pick the hash function based on the names of your friends, right? Presumably Apple and Google and others already chose their hash function independent of what your friends' names are. So ideally, they want to pick a hash function that generally is quite fast, big O of 1. But practically speaking, in a hash table, unless you get really lucky with the inputs, which you generally won't, really it's big O of n running time. Why? Because in the worst possible scenario, you might have one long linked list. But in practice, ideally, and this is a little naive, but suppose that you have a uniform distribution of friends in the world where 1/26 of them have names starting with A, and then another 1/26 out of B, and then ... Z. That would be a nice uniform distribution of friends. Technically, then, your running time of a hash table for searching it or deleting or inserting would technically be big O of n divided by k, where k is the number of buckets, a constant. So it's technically big O of n divided by 26. Now, again, per our discussion of big O notation, that's still the same thing, right? You get rid of constant factors. So yes, it's 26 times faster. The chains are 1/26 the length. But asymptotically, in terms of big O notation, it's still big O of n. And here's where now we can start to veer away from like what is theoretically right versus what is practically right. In reality, in the real world, if you work for Google, Microsoft, Apple, and others, 26 times faster is actually faster in the real world, even though a mathematician might say, that's really the same thing. But it's not. Like the real world wall clock time, if you watch the number of seconds passing on the clock, n over k is a much better running time than big O of n. So here, too, we're getting to the point where the conversations need to become a little more sophisticated. It's not quite as simple as theory versus practice. It depends on what matters ultimately to you. But ideally, and literally, if somehow or other they picked an ideal hash function, big O of 1 would really be the ideal here, would really be the running time we achieve. And what you'll generally find in the real world is that you don't use hash functions that are as simplistic as just look at the first letter. And honestly, they won't generally look at the first and the second and the third letter. They'll use some even fancier math to put real downward pressure on the probability of collisions so that, yes, they will still happen. But most of the time, a really good hash function, even if it's not quite ideal, will be darn close to constant time, which makes hash tables and in turn dictionaries one of the most universally compelling data structures to use. Now, with that said, we have time for just another data structure or so. And this is not a typo. This one's called a trie. And a trie is short for retrieval, which is weird because you say retrieval, but we say trie. But that's the etymology of trie. And a trie is sort of of the weirdest amalgamation of all of these things, whereby a trie is a tree of arrays. So a hash table is an array of linked lists. A trie is a tree of arrays. So at some point, computer scientists just started like mashing together all of these different inputs and let's see what comes out of it. But a trie is actually really interesting. And what you're about to see is a data structure that is literally big O of one time, constant time, but there is a downside. So in a trie, every node is an array, and every location in that array generally represents a letter of the alphabet. You could generalize this away from words too. But a trie, in this case, if we have a root node, that root root node is technically a big array with 26 locations. And if you want to insert names or words more generally into a trie, what you do is this. You hash again and again and again, creating one array for every letter in your word. So what do I mean by that? If we've got 26 elements here, this would be representing A, this would be representing Z, and initially these are all null by default when you have just this root. But suppose I want to insert a few friends of mine, including Toad, for instance. T-O-A-D is the name. So how would I do that? I would first find the location for T based on its number, 0 through 25. And if this is T, what would I then do? I would change the null to actually be a pointer to another node, aka another array. And then I would go into the second array and hash on the second letter of Toad's name, which is, of course, O. And then I would set a pointer to a third node in my tree, which would be represented here. So another 26 pointers. Then I would find the pointer representing A. And I would create finally a fourth node, another array, representing the fourth letter of Toad's name. But because Toad's name ends with D, and therefore I already have 4 nodes here, we need to specially color, though we could probably use an actual variable here. I need to somehow indicate that Toad's name stops here. So it's not null per se. This actually means that T-O-A-D is in this data structure. But I did this deliberately because another friend of mine might be Toadette in the Nintendo world. And Toadette, of course, is a superstring of Toad. That is, it's longer, but it shares a common prefix. So Toadette could continue, and I could have another node for the E, another node for the T, another node for the second T, and another node for the last E. But I somehow have to sort of mark that E is the end of her name as well. So even though they share a common prefix, the fact that there's 2 green boxes on the screen means that T-O-A-D is in this dictionary as a key, as is T-O-A-D-E-T-T-E is another key. And technically speaking, what's in these boxes too, it's not just a pointer, it's probably Toad and Toadette's phone number and email address and like the actual value of the dictionary. Which is to say, this too is in fact a dictionary. A dictionary is just an abstract data type, a collection of key value pairs, just like I claimed a stack and a queue was, and how you implement it can differ. You could implement it with a hash table, an array of linked lists as we just did, or you can implement a dictionary as a trie, a tree of arrays. And let me add one more name to the mix. Tom, for instance, a valid name from the universe, T-O-M, just means that, OK, that name exists in this structure as well. Now, what is the implication of storing the names in this way, which is sort of implicitly? Like I'm effectively storing Toad and Toadette and Tom in this data structure without actually storing T or O or A or D or any of the other letters. I'm just implicitly storing those letters by actually using valid pointers that lead to another node. And so what's the implication of this in code? Well, in code, it might look like this. Every node in a trie is now redefined as being an array of size 26, and I'll call it children, just to borrow the family tree metaphor, and that in each of these nodes, there is room for the person's phone number, for instance, aka a string or char star. So what does this mean? Well, if there's actually a non-null number there, that's equivalent to there being a green box. Like if you actually see +1 617 dash whatever there, that means there's a green box because Toad's number is right here, or Toadette's number is down here, or Tom's is over there. But if this is null, that just means that maybe this is the T or the O or the E, which are not actually ends of people's names. So that's all these nodes actually are. And if we think back now to what this data structure looks like, this is, in fact, a data structure that can be navigated in constant time. Why? Well, all we need to keep track of this data structure is literally one pointer called trie that's a pointer to the first of these nodes, the so-called root of the trie. And when it comes to now thinking about the running time of a trie, well, what is it? Well, if you've got n friends in your contacts already, or if there's n keys in that data structure, how many steps does it take to find anyone? Well, whether I have 3 names, Toad, Toadette, or Tom, or 3 million names in that data structure, how many steps will it take me to find Toad ever? T-O-A-D. How many steps for Toadette? T-O-A-D-E-T-T-E. 8 steps. How about for Tom? 1, 2, 3. And frankly, I'm sure if we looked it up, there's probably a limit on the number of characters in a Nintendo character's name. Maybe it's 20 characters total, or maybe a little longer, 30. There's some fixed value. It's not unbounded. There's not an infinite number of letters in any Nintendo character's name. So there's some constant value, call it K. So no matter whose name you're looking for, it's going to take you maximally k steps, but k is a constant. And we have always said that big O of k is the same thing as big O of 1. So for all intents and purposes, even though we're taking a bit of liberty here, searching a trie, inserting into a trie, deleting from a trie is constant time. Because if you have a billion names in the dictionary already, it's going to take up a huge amount of space, but it does not affect how many steps it takes to find Toad or Toadette or Tom. That depends only on the length of their names, which effectively is a constant value. But there is a downside here, and it's kind of a big one. In practice, I dare say most computers, most systems would actually use hash tables, not tries, to implement dictionaries, collections of key value pairs. What's the downside of this here data structure, might you think? And this is just a representative picture for Toad, Tom, and Toadette. All the space it takes up. I mean, even for these three names, look at how many empty pointers there are. So they're null, to be sure, but there's like 25 unused spaces here, another 25 unused spaces here, 24 unused spaces here. And what's not pictured is if I've got more and more names, this thing's just going to blow up with more and more and more and more arrays, even though there's not going to be someone whose name starts with like LAA or LBA or LBB. There's going to be so many combinations of letters where it's just going to be null pointers instead. So it takes up a huge amount of space, but it does give us constant time. And that then is this here trade-off. So I would encourage you here on out, as we exit the world of C, and so much of today's code and the past several weeks' code will soon be reduced in a week's time to just 1 line of code, 2 lines of code, because Python and the authors of Python will have implemented all of this week's and last week's and prior week's ideas for us. We'll be able to operate at a higher level of abstraction and just think about what problems we want to solve and how we want to do so algorithmically and with data structures. And data structures, in conclusion, are everywhere. Has anyone recognized this spot in Harvard Square? Anyone? What are we looking at? So this is Sweetgreen, a popular salad place. And this is actually a dictionary, or really a hash table of sorts. Why? Well, if you buy a very expensive salad at Sweetgreen and they put it on the shelf for you, if you've ordered via the app or online in advance, and if I, for instance, were to order a salad, it would probably go under the D heading. If Carter were to order a salad, it would go under C, Yulia under Y. And so they hash the salads based on your first name to a particular location on the shelf. Why is that a good thing? Well, if it were just one long shelf that wasn't even alphabetical, it would be big O of N for me to find my salad and for Carter and Yulia to find theirs. Because they've got 26 letters here, it's big O of 1. It's one step for any of us to find our salads, except, again, in perverse situations, where to might this system devolve? At like 12:30 p.m. in the afternoon, for instance. What could go wrong? Yeah, a lot of people with the same first letters of their names might order a salad. So there's lots of like D, 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 D. Where do we put the next person? OK, well, maybe we overflow to E. What if there's a lot of E people? It overflows to F. What if it overflows to then we go to G? And it sort of devolves anyway into a linked list or really multiple arrays that you have to search in big O of N time. I've even been to Sweetgreen at non-popular times. And sometimes the staff just don't even choose to use the dictionaries. They just put it like what's closest to them. So you have to search the same thing anywhere. But you'll start to see, now that you've seen some of these building blocks, that like data structures are everywhere, algorithms are everywhere, and among the goals of CS50 now are to harness these ideas most efficiently. So that's a wrap. We'll see you next time.
Downside.
Learn a little bit about trees and heaps, but really these all just end up being variations on a theme. There really are these kind of 4 basic ideas that sort of everything else can boil down to: arrays, linked lists, hash tables, and tries. And like I said, there are variations on them. But this is pretty much going to summarize everything we're going to talk about in this class in terms of C. But we're going to talk about in this class in terms of C. But how do these... We're going to talk about in this class in terms of C. But how do these all measure up, right? We've talked about the pros and cons of each sort of in separate videos on them, but there's a lot of numbers getting thrown around. There's a lot of general thoughts getting thrown around. Let's try and consolidate it into just one place. Let's weigh the pros against the cons and consider which data structure might be the right data structure for your particular situation, whatever kind of data you're storing. You don't necessarily always need to use the super fast insertion, deletion, and lookup of a try. If you really don't care about inserting and deleting too much, if you need to just quickly random access, maybe an array is better. So let's distill that, right? Let's talk about each of the 4 major kinds of data structures that we've talked about, and just see when they might be good and when they might not be so good. So we'll start with arrays. So insertion, that's kind of bad. Insertion at the end of an array is okay, if we're building an array as we go. But if we need to insert elements into the middle, think back to insertion sort, there's a lot of shifting to fit an element in there. And so if we're going to insert anywhere but the end of an array, that's probably not so great. Similarly, deletion, unless we're deleting from the end of an array, is probably also not so great if we don't want to leave empty gaps, which usually we don't. We want to remove an element and then sort of make it snug again. And so deleting elements from an array, also not so great. Lookup, though, is great. We have random access, constant time lookup. We just say 7, and we go to array location 7. We say 20, we go to array location 20. We don't have to iterate across. That's pretty good. Arrays are also relatively easy to sort, and every time we talked about a sorting algorithm, such as selection sort, insertion sort, bubble sort, merge sort, we always used arrays to do it, because arrays are pretty easy to sort relative to the data structures we've seen so far. They're also relatively small. There's not a lot of extra space. You just set aside exactly as much as you need to hold your data, and that's pretty much it. So they're pretty small and efficient in that way. But another downside, though, is that they are fixed in size. We have to declare exactly how big we want our array to be, and we only get one shot at it. We can't grow and shrink it. If we need to grow or shrink it, we need to declare an entirely new array, copy all of the elements of the first array into the second array, and if we miscalculated that time, we need to do it again. Not so great. So arrays don't give us the flexibility to have variable numbers of elements. With a linked list, insertion is pretty easy, right? We just tack on to the front. Deletion is also pretty easy. We have to find the elements. That involves some searching. But once you've found the element you're looking for, all you need to do is change a pointer, possibly 2 if you have a linked list, a doubly linked list rather, and then you can just free the node. You don't have to shift everything around. You just change 2 pointers. So that's pretty quick. Lookup is bad though, right? In order for us to find an element in a linked list, whether singly or doubly linked, we have to linear search it. We have to start at the beginning and move to the end, or start at the end and move to the beginning. We don't have random access anymore. So if we're doing a lot of searching, maybe a linked list isn't quite so good for us. They're also really difficult to sort, right? The only way you can really sort a linked list is to sort it as you construct it. But if you sort it as you construct it, you're no longer making quick insertions anymore. You're not just tacking things onto the front. You have to find the right spot to put it. And then your insertion becomes just about as bad as inserting into an array. So linked lists are not so great for sorting data. They're also pretty small size-wise. Doubly linked lists slightly larger than singly linked lists, which are slightly larger than arrays, but it's not a huge amount of wasted space. So if space is at a premium, but not a really intense premium, might be the right way to go. Hash tables. Insertion into a hash table is fairly straightforward. It's a two-step process. First, we need to run our data through a hash function to get a hash code, and then we insert the element into the hash table at that hash code location. Deletion, similar to linked list, is easy once you find the element. You have to find it first, but then when you delete it, you just need to exchange a couple of pointers if you're using separate chaining. If you're using probing or if you're not using chaining at all in your hash table, deletion is actually really easy. All you need to do is hash the data and then go to that location. And assuming you don't have any collisions, you'll be able to delete very quickly. Now, lookup is where things get a little more complicated, right? So it's on average better than linked lists. If you're using chaining, you still have a linked list, which means you still have the search detriment of a linked list. But because you're taking your linked list and splitting it over 100 or 1,000 or n elements in your hash table, your linked lists are all 1/n the size, right? They're all substantially smaller. You have n linked lists instead of one linked list of size n. And so this real world constant factor, which we generally don't talk about in time complexity, it does actually make a difference here. So lookup is still linear search if you're using chaining, but the length of the list you're searching through is very, very short by comparison. Again, if sorting is kind of your goal here, hash table is probably not the right way to go. Just use an array if sorting is really important to you. And they can sort of run the gamut of size. It's hard to say whether a hash table is small or big because it really depends on how large your hash table is. If you're only going to be storing 5 elements in your hash table, and you have a hash table with 10,000 elements in it, you're probably wasting a lot of space. Contrast being, you can also have very compact hash tables, but the smaller your hash table gets, the longer each of those linked lists gets. And so there's really no way to define exactly the size of a hash table, but it's probably safe to say it's generally going to be bigger than a linked list of storing the same data, but smaller than a trie. And tries are sort of the fourth of these structures that we've been talking about. Inserting into a trie is complex. There's a lot of dynamic memory allocation, especially at the beginning as you're starting to build, but it's constant time. It's only the human sort of element here that makes it tricky. Having to encounter a null pointer, malloc space, go there, possibly malloc space from there again. This sort of intimidation factor of pointers in dynamic memory allocation is the hurdle to clear. But once you've cleared it, insertion actually becomes quite simple, and it certainly is constant time. Deletion is easy. All you need to do is navigate down a couple of pointers and free the node, so that's pretty good. Lookup is also pretty fast. It's only based on the length of your data. So if all of your data is 5-character strings, for example, you're storing 5-character strings in your trie, it only takes 5 steps to find what you're looking for. 5 is just a constant factor. So again, insertion, deletion, and lookup here are all constant time effectively. Another thing is that your trie is actually kind of already sorted, right? By virtue of how we're inserting elements by going letter by letter of the key or digit by digit of the key, typically, your trie ends up being kind of sorted as you build it. It doesn't really make sense to think about sorting in the same way that we think about it with arrays or linked lists or hash tables, but in some sense, your trie is sorted as you go. The downside, of course, is that a trie rapidly becomes huge. From every junction point, you might have, if your key consists of digits, you have 10 other places you can go, which means that every node contains information about the data you want to store at that node, plus 10 pointers, which on CS50 IDE is 80 bytes. So it's at least 80 bytes for every node that you create, and that's not even counting data. And if your nodes are letters instead of digits, now you have 26 pointers from every location, and 26 times 8 is probably 200 bytes or something like that. And if you have capital and lowercase, you can see where I'm going with this, right? Your nodes can get really big, and so the trie itself overall can get really big too. So if space is at a high premium on your system, a trie might not be the right way to go, even though its other benefits come into play. I'm Doug Lloyd. This is CS50. We surely can do more. Indeed, bools. But that doesn't limit everything that we can do. We surely can do more. Indeed, with structures, that gives us an ability to start to define our own data types that might be useful for our own programs. What's cool about structures is they allow us to unify many different variables of different data types into a single brand new type. And we can give that new type its own unique type name as a way to identify it. This isn't the first time we've seen its own unique type name as a way to identify it. This isn't the first time we've seen the ability to combine multiple variables together. We've seen that with arrays. But remember, the restriction with arrays is that we can only combine things of the same type. We can have a whole bunch of integers or a whole bunch of floats, but we can't mix them up. With structures, we actually can. We can group together elements that have a logical connection to one another. So for example, we can group together a structure for, like, say, a student, where a student would have an ID number, which is probably an integer. But they also have a name, which is a string, and they might have a GPA, which is a float. And we can have all of these things tied together in basically what's a super variable. It's a variable that has other variables within it. The way to do this in C is actually pretty straightforward. Some syntax might look like this. Instead of a student in this example, let's use a car. We introduce the concept of a structure by saying struct. We're about to define a structure type. And in particular, we're going to define a struct car. And struct car actually now becomes our type name. It's not just car, it's struct car. Inside of the curly braces from this point forward, we can define all of the different variables that we want inside of our super variable. So for example, here are some things that are common to cars. They have a year, the year that they were manufactured. We have a model and a license plate and an odometer, which is a number of miles. And maybe they have an engine size, which in the United States is usually represented as a float for how many liters the engine capacity is. And notice that these are all different data types being mixed together. We have integers, and we have two strings, and we have a float or a double, all mixed up inside of one super variable. To finish our definition of this structure, we have a closing curly brace, and then really important, a common syntax error, is a semicolon at the end, which completes our definition of a struct car. Once we define the structure, and usually we define our structure at the very top of our program, up near our pound includes and our pound defines, but we also might define them in a separate .h file, because maybe we're using this type definition in several different files or several different programs, and so it makes sense to define it somewhere outside of a single file and have it be a .h file that we can pound include in multiple different contexts. Now we have effectively created this new type, and we can start to use it. And we can create variables of this type just like we can create variables of any other type. Int x, that's how we create an integer called x. Struct car y, that's how we create a variable called y of type struct car. So that's how we create the variable overall. How do we create the individual fields or members of that, or rather, how do we access the individual fields or members of that structure? Well, we can do so using something called the dot operator. Let's take a look at what that looks like. So at the top here, I have a variable declaration, struct car my car. Again, here the type is struct car, and the variable name is my car. From this point forward, whenever I want to refer to a field or a member within my car, which is again the variable name, I can use the dot operator to access those individual fields within my car. So I could say, for example, mycar.year equals 2011. I can't just say year equals 2011. Year is something that is part of my car, so I have to always refer to it in the context of my car. I can say stir copy mycar.plate CS50. Remember, it's a string. I can't just assign it. I have to copy that string into the variable. I can say mycar.odometer equals 50505, or anything else that I want to do. I can set the engine size, and I can set the model. I can do whatever else I want to do just by accessing the fields similar to this. But structures, like variables of all other data types, we don't have to just use the stack for this. We don't just have to say struct car, mycar, semicolon. We could dynamically allocate this if we don't know at the beginning of our program, for example, that we're going to need a certain number of these things. We can just declare this on the fly dynamically using pointers, of course. In order to access our fields in that situation, we don't use just the dot operator because we have a pointer to a structure. We also have to first, as you may recall, dereference that pointer and then access its fields. It adds a little bit of extra stuff, but let's take a look again here. So here now, instead of statically declaring a struct car called mycar, I'm going to dynamically allocate a struct car called mycar. So struct car star mycar, and then I'm going to malloc space for a struct car. And here's a cool thing about size of. Size of is not just built in. It doesn't just happen to know just the size of integers, characters, floats, and doubles. It can also figure out on the fly exactly how much space is required for a struct car. So you don't have to go through and figure out like, okay, well, this is probably like 30 bytes or something. You can just say size of struct car and let the computer figure it out for you. So struct car star mycar equals malloc size of struct car. That dynamically allocates on the heap one chunk of memory large enough to hold a single struct car within it. And then I can access my fields by first dereferencing the pointer. And then once I've dereferenced the pointer, I can then use the dot operator to access the fields. Again, it's very similar to what we just saw, but the syntax here is a little cumbersome, right? Now we have extra parentheses, we have this star, we have this dot. Surely there's got to be an easier way. C programmers love for there to be easier ways to do things, and in fact, there is a shortcut for this. It so happens that accessing the field of a structure via its pointer is a common enough operation that there is an entirely different operator that allows us to do this much more succinctly, and it is called the arrow operator, which is just a hyphen and then a greater than symbol, literally making it look like it's an arrow. It does two operations back to back. So for the first thing it does is it dereferences the pointer, which is on the left of the arrow, and then it's going to access the field, which is on the right of the arrow. So for example, this is what the code looked like before. This is what we just had on the slide a second ago, where I'm dereferencing pointers, and then I'm using the dot operator to access the fields. Here's what the same code would look like with the arrow syntax. And the same thing is happening here. The first thing I'm doing is I'm dereferencing my car, but the arrow operator does that for me. I don't have to use the star syntax. It just knows if I have an arrow there, I need to first dereference the thing on the left, and then I can access the field on the right. So using the arrow operator is a great way to have a shorthand for accessing the field of a structure to which you only have a pointer. And you'll probably use this a fair amount. So it's syntax definitely to befriend and to get used to. I'm Doug Lloyd. This is CS50. So for the first thing, using the dot operator, it does is it dereferences. This is what the code looked like before. This is what we just had on the slide a second ago, where I'm dereferencing pointers, and then I'm using the dot operator to access the fields. Here's what the same code would look like. Sorry, I left you off on a bit of a cliffhanger, but I'm glad you're here to finish the story of doubly linked lists. So if you recall from that video, we talked about how singly linked lists do extend our ability to deal with information where the number of elements or the number of items in a list can grow or shrink. We can now deal with something like that where we couldn't deal with it with arrays. But they do suffer from one critical limitation, which is that with a singly linked list, we can only ever move in a single direction through the list. And the only real situation where that became a problem was when we were trying to delete a single element. And we didn't even discuss how to do it in a singly linked list. In pseudocode, it is certainly doable, but it can be a bit of a hassle. So if you find yourself in a situation where you're trying to delete single elements from the list, or it's going to be required that you'll be deleting single elements from the list, you might want to consider using a doubly linked list instead of a singly linked list, because doubly linked lists allow you to move both forwards and backwards through the list instead of just forwards through the list, just by adding one extra element to our structure definition for the doubly linked list node. Again, if you're not going to be deleting single elements from the list, because we're adding an extra field to our structure definition, the nodes themselves for doubly linked lists are going to be larger. They're going to take up more bytes of memory. And so if this is not something you're going to need to do, you might decide it's not worth the trade-off to have to spend the extra bytes of memory required for a doubly linked list if you're not going to be deleting single elements. But they're also cool for other things too. So as I said, we just have to add one single field to our structure definition, this notion of a previous pointer. So with a singly linked list, we had the value and the next pointer. So the doubly linked list just has a way to move backwards as well. Now, in the singly linked list video, we talked about these are 5 of the main things you need to be able to do to work with linked lists. And for most of these, the fact that it's a doubly linked list isn't really a big jump. We can still search through by just moving forward from start to end. We can still create a node out of thin air pretty much the same way. We can delete lists pretty much the same way too. The only things that are slightly different really are inserting new nodes into the list, and we'll finally talk about deleting a single element from the list as well. Again, pretty much the other 3, we're not going to talk about them right now because they're just very minor tweaks on the ideas discussed in the singly linked lists video. So let's insert a new node into a doubly linked list. We talked about doing this for singly linked lists as well, but there's a couple of extra catches with doubly linked lists. We're passing in the head of the list here and some arbitrary value, and we want to get the new head of the list out of this function. That's why it returns a DLL node star. So what are the steps? They're again very similar to singly linked lists with one extra addition. We want to allocate space for a new node and check to make sure it's valid. We want to fill that node up with whatever information we want to put in it. The last thing we need to do, the extra thing we need to do rather, is to fix the previous pointer of the old head of the list. Remember that because of doubly linked lists, we can move forward and backward, which means that each node actually points to 2 other nodes instead of just one. And so we need to fix the old head of the list to point backward to the new head of the linked list, which is something we didn't have to do before. And then, as before, we just return a pointer to the new head of the list. So here's a list. We want to insert 12 into this list. Notice that the diagram is slightly different, right? Each node contains 3 fields, data, and a next pointer in red, and a previous pointer in blue. Nothing comes before the 15 nodes, so its previous pointer is null. It's the beginning of the list. There's nothing before it. And nothing comes after the 10 node, and so its next pointer is null as well. So let's add 12 to this list. We need malloc space for the node. We put 12 inside of it. And then, again, we need to be really careful not to break the chain. We want to rearrange the pointers in the correct order. And again, we put 12 inside of it. And then, again, we put 12 inside of it. And then, again, we need to be really careful not to break the chain. We want to rearrange the pointers in the correct order. And sometimes that might mean, as we'll see, particularly with delete, that we do have some redundant pointers, but that's okay. So what do we want to do first? I would recommend that the things you should probably do are to fill the pointers of the 12 node before you touch anybody else. So what is 12 going to point to next? 15. What comes before 12? Nothing. Now we've filled the extra information in 12, so it has previous, next, and value. Now we can have 15, this extra step we were talking about, we can have 15 point back to 12. And now we can move the head of the linked list to also be 12. So that's pretty similar to what we were doing with singly linked lists, except for accounting for the extra step of connecting the old head of the list back to the new head of the list. Now let's finally delete a node from a linked list. So let's say we have some other function that is finding a node we want to delete and has given us a pointer to exactly the node that we want to delete. We don't even need, say the head is still, globally declared. We don't need head here. All this function is doing is we found a pointer to exactly the node we want to get rid of. Let's get rid of it. It's a lot easier with doubly linked lists. First, it's actually just a couple of things. We just need to fix the surrounding nodes pointers so that they skip over the node we want to delete, and then we can delete that node. So again, we're just going through here. We have apparently decided that we want to delete the node X. And again, what I'm doing here, by the way, is a general case for a node that is in the middle. There are a couple of extra caveats that you need to consider when you're deleting the very beginning of the list or the very end of the list. There's a couple of special corner cases to deal with there. So this works for deleting the any node in the middle of the list, one that has a legitimate pointer forward and a legitimate pointer backward, legitimate previous and next pointer. Again, if you're working with the ends, you need to handle those slightly differently, and we're not going to talk about that now, but you can probably figure out what needs to be done just by watching this video. So we've isolated X. X is the node we want to delete from the list. What do? First, we need to rearrange the outside pointers. We need to rearrange 9's next to skip over 13 and point to 10, which is what we've just done. And we also need to rearrange 10's previous to point to 9 instead of pointing to 13. So again, this was the diagram to start with. This was our chain. We need to skip over 13, but we need to also preserve the integrity of the list. We don't want to lose any information in either direction. So we need to carefully rearrange the pointers carefully so we don't break the chain at all. So we can say 9's next pointer points to the same place that 13's next pointer points right now, because we're eventually going to want to skip over 13. So wherever 13 points next, we want 9 to point there instead. So that's that. And then wherever 13 points back to, whatever comes before 13, we want 10 to point to that instead of 13. Now notice if you follow the arrows, we can drop 13 without actually losing any information. We've kept the integrity of the list moving both forward and backward. And then we can just sort of clean it up a little bit by pulling the list together. And we rearranged the pointers on either side, and then we freed X, the node that contained 13, and we didn't break the chain. So we did good. Final note here on linked lists. So both singly and doubly linked lists, as we've seen, support really efficient insertion and deletion of elements. You can pretty much do it in constant time. What do we have to do to delete an element just a second ago? We moved one pointer, we moved another pointer, we freed X. Took 3 operations. It always takes 3 operations to delete that node, to free a node. How do we insert? Well, we're just always tacking on at the beginning if we're inserting efficiently. So we need to rearrange, depending on if it's a singly or a doubly linked list, we might need to do 3 or 4 operations max. But again, it's always 3 or 4. It doesn't matter how many elements are in our list, it's always 3 or 4 operations, just like deletion is always 3 or 4 operations. It's constant time. So that's really great, right? With arrays, if we're doing something like insertion sort, you probably recall that insertion sort is not a constant time algorithm. It's actually pretty expensive. So this is a lot better for inserting. But as I mentioned in the singly linked list video, we've got a downside here too, right? We've lost the ability to randomly access elements. We can't say I want element number 4 or element number 10 of a linked list the same way that we can do that with an array, where we can just directly index into our array's elements. And so trying to find an element in a linked list, if searching is important, may now take linear time. As the list gets longer, it might take one additional step for every single element in the list in order to find what we're looking for. So there's trade-offs, right? There's a bit of a pro and a con element here. And doubly linked lists are not the last kind of data structure combination that we'll talk about, taking all the basic building blocks of C and putting them together, because in fact we can even do better than this to create a data structure that you might be able to search through in constant time too. But more on that in another video. I'm Doug Lloyd. This is CS50. By now, you know a lot about arrays, and you know a lot about linked lists. And we've discussed the pros and the cons. We've discussed that linked lists can get bigger and smaller, but they take up more size. Arrays are much more straightforward to use, but they're restrictive in as much as we have to set the size of the array at the very beginning, and then we're stuck with it. But we've pretty much exhausted all of our topics about linked lists and arrays. Or have we? Maybe we can do something even more creative. And this sort of lends to the idea of a hash table. So in a hash table, we're going to sort of try and combine an array with a linked list. We're going to take the advantages of the array, like random access, being able to just go to array element 4 or array element 8 without having to iterate across. That's pretty fast, right? But we also want to have our data structure be able to grow and shrink. We don't want to be restricted. And we want to be able to add and remove things very easily, which, if you recall, is very complex with an array. And we can call this new thing a hash table. And if implemented correctly, we're sort of taking the advantages of both data structures we've already seen, arrays and linked lists. On average, insertion into a hash table can start to get close to constant time. And deletion can get close to constant time. And lookup can get close to constant time. We don't have a data structure yet that can do that. And so this already sounds like a pretty great thing. We've really mitigated the disadvantages of each on its own. To get this performance upgrade, though, we need to rethink how we add data into the structure. Specifically, we want the data itself to tell us where it should go in the structure. And if we then need to see if it's in the structure, if we need to find it, we want to look at the data again and be able to effectively, using the data, randomly access it. Just by looking at the data, we should have an idea of where exactly we're going to find it in the hash table. Now, the downside of a hash table is that they're really pretty bad at ordering or sorting data. And in fact, if you start to use them to order or sort data, you lose all of the advantages you previously had in terms of insertion and deletion. The time becomes closer to theta of n, and we've basically regressed into a linked list. And so we only want to use hash tables if we don't care about whether data is sorted. For the context in which you'll use them in CS50, you probably don't care that the data is sorted. So a hash table is a combination of two distinct pieces with which we're familiar. The first is a function, which we usually call a hash function. And that hash function is going to return some non-negative integer, which we usually call a hash code. Okay? The second piece is an array, which is capable of storing data of the type we want to place into the data structure. We'll hold off on the linked list element for now and just start with the basics of a hash table to sort of get your head around it, and then we'll maybe blow your mind a little bit when we combine arrays and linked lists together. The basic idea, though, is we take some data, we run that data through the hash function, and so the data is processed and it spits out a number, okay? And then with that number, we just store the data we want to store in the array at that location. So for example, we have maybe this hash table of strings. It's got 10 elements in it, so we can fit 10 strings in it. Let's say we want to hash John. So John is the data we want to insert into this hash table somewhere. Where do we put it? Well, typically with an array so far, we probably would just put it in array location 0. But now we have this new hash function. And let's say that we run John through this hash function and it spits out 4. Well, that's where we're going to want to put John. We want to put John in array location 4. Because if we hash John again, let's say later we want to search and see if John exists in this hash table, all we need to do is run it through the same hash function, get the number 4 out, and we'll be able to find John immediately in our data structure. So that's pretty good. Let's say we now do this again. We want to hash Paul. We want to add Paul into this hash table. Let's say that this time we run Paul through the hash function. The hash code that is generated is 6. Well, now we can put Paul in array location 6. And if we need to look up whether Paul is in this hash table, all we need to do is run Paul through the hash function again. And we're going to get 6 out again. And then we just look at array location 6. Is Paul there? If so, he's in the hash table. Is Paul not there? He's not in the hash table. It's pretty straightforward. Now, how do you define a hash function? Well, there's really no limit to the number of possible hash functions. In fact, there's a number of really, really good ones on the internet. There's a number of really, really bad ones on the internet. It's also pretty easy to write a bad one. So what makes up a good hash function, right? Well, a good hash function should use only the data being hashed and all of the data being hashed. So we don't want to use anything, we don't want to incorporate anything else other than the data. And we want to use all of the data. We don't just want to use a piece of it, we want to use all of it. A hash function should also be deterministic. What does that mean? Well, it means that every time we pass the exact same piece of data into the hash function, we always get the same hash code out. If I pass John into the hash function and I get out 4, I should be able to do that 10,000 times and I'll always get 4. So no random numbers effectively can be involved in our hash tables, in our hash functions. A hash function should also uniformly distribute data. If every time you run data through the hash function you get the hash code 0, that's probably not so great, right? You probably want a big range of hash codes so things can be spread out throughout the table. And also it would be great if really similar data like John and Jonathan maybe were spread out to way different locations in the hash table. That would be a nice advantage. Here's an example of a hash function. I wrote this one up earlier. It's not a particularly good hash function for reasons that don't really bear going into right now, but do you see what's going on here? It seems like we're declaring a variable called sum and setting it equal to 0, and then apparently I'm doing something so long as str square bracket j is not equal to \0. Well, what am I doing there? This is basically just another way of implementing strlen, detecting when you've reached the end of the string. So I don't have to actually calculate the length of the string. I'm just using when I hit the \0 character, I know I've reached the end of the string. And then I'm going to keep iterating through that string, adding strj to sum. And then at the end of the day, I'm going to return sum mod hash max. Well, basically all this hash function is doing is adding up all of the ASCII values of my string, and then it's returning some hash code modded by hash max, which is probably the size of my array, right? I don't want to be getting hash codes if my array is of size 10. I don't want to be getting out hash codes 11, 12, 13. I can't put things into those locations of the array. That would be illegal. I'd suffer a segmentation fault. Now, here's another quick aside. Generally, you're probably not going to want to write your own hash functions. It is actually a bit of an art, not a science, and there's a lot that goes into them. The internet, like I said, is full of really good hash functions, and you should use the internet to find hash functions, because it's really just kind of an unnecessary waste of time to create your own. You can write simple ones for testing purposes, but when you actually are going to start hashing data and storing it into a hash table, you're probably going to want to use some function that was generated for you that exists on the internet. If you do, just be sure to cite your sources. There's really, there's no reason to plagiarize anything here. The computer science community is definitely growing and really values open source. And it's really important to cite your sources so that people can get attribution for the work that they're doing to the benefit of the community. So always be sure, and not just for hash functions, but generally, when you use code from an outside source, always cite your source. Give credit to the person who did some of the work so you don't have to. OK, so let's revisit this hash table for a second. This is where we left off after we inserted John and Paul into this hash table. Do you see a problem here? You might see two. But in particular, do you see this possible problem? What if I hash Ringo, and it turns out that after processing that data through the hash function, Ringo also generated the hash code 6. I've already got data at array location 6, so it's probably going to be a bit of a problem for me now, right? We call this a collision, and a collision occurs when two pieces of data run through the same hash function yield the same hash code. Presumably, we still want to get both pieces of data into the hash table. Otherwise, we wouldn't be running Ringo arbitrarily through the hash function. We presumably want to get Ringo into that array. How do we do it, though, if he and Paul both yield hash code 6? We don't want to overwrite Paul. We want Paul to be there, too. So we need to find a way to get elements into the hash table that still preserves our quick insertion and quick lookup. And one way to deal with it is to do something called linear probing. Using this method, if we have a collision, well, what do? Well, if we can't put him in array location 6 or whatever hash code was generated, let's put him at hash code +1. And if that's full, let's put him in hash code +2. The benefit of this being, if he's not exactly where we think he is, and we have to start searching, maybe we don't have to go too far. Maybe we don't have to search all n elements of the hash table. Maybe we only have to search a couple of them. And so we're still tending towards that average case being close to 1 versus close to n. So maybe that'll work. So let's see how this might work out in reality, and let's see if maybe we can detect the problem that might occur here. Let's say we hash BART. So now we're going to run a new set of strings through the hash function. And we run BART through the hash function. We get hash code 6. We take a look. We see 6 is empty, so we can put BART there. Now we hash Lisa, and that also generates hash code 6. Well, now that we're using this linear probing method, we start at 6. We see that 6 is full. We can't put Lisa in 6. So where do we go? Let's go to 7. 7's empty, so that works. So let's put Lisa there. Now we hash Homer, and we get 7. OK, well, we know that 7's full now, so we can't put Homer there. So let's go to 8. Is 8 available? Yeah, and 8's close to 7, so if we have to start searching, we're not going to have to go too far. And so let's put Homer at 8. Now we hash Maggie and returns 3. Thank goodness, we're able to just put Maggie there. We don't have to do any sort of probing for that. Now we hash Marge, and Marge also returns 6. Well, 6 is full, 7 is full, 8 is full, 9, all right, thank God, 9 is empty. I can put Marge at 9. Already we can see that we're starting to have this problem where now we're starting to stretch things kind of far away from their hash codes, and that theta of 1, that average case of being constant time, is starting to get a little more, starting to tend a little more towards theta of n, and we're starting to lose that advantage of hash tables. This problem that we just saw is something called clustering. And what's really bad about clustering is that once you now have 2 elements that are side by side, it makes it even more likely. You have double the chance that you're going to have another collision with that cluster, and the cluster will grow by 1. And you'll keep growing and growing your likelihood of having a collision. And eventually, it's just as bad as not sorting the data at all. The other problem, though, is we still, and so far up to this point where we've just been sort of understanding what a hash table is, we still only have room for 10 strings. If we want to, continue to hash the citizens of Springfield, we can only get 10 of them in there. And if we try and add an 11th or a 12th, we don't have a place to put them. We could just be spinning around in circles trying to find an empty spot, and we would maybe get stuck in an infinite loop. So this sort of lends to the idea of something called chaining, and this is where we're going to bring linked lists back into the picture. What if instead of storing just the data itself in the array, every element of the array could hold multiple pieces of data? Well, that doesn't make sense, right? We know that an array can only hold, each element of an array can only hold one piece of data of that data type. But what if that data type is a linked list, right? So what if every element of the array was a pointer to the head of a linked list? And then we could build those linked lists and grow them arbitrarily, because linked lists allow us to grow and shrink a lot more flexibly than an array does. So what if we now we leverage this, right? We start to grow these chains out of these array locations. Now we can fit an infinite amount of data, or not infinite, but an arbitrary amount of data into our hash table without ever running into the problem of collision. We've eliminated clustering by doing this. And well, we know that when we insert into a linked list, if you recall from our video on linked lists, singly linked lists, and doubly linked lists, it's a constant time operation. We're just adding to the front. And for lookup, well, we do know that lookup in a linked list can be a problem, right? We have to search through it from beginning to end. There's no random access in a linked list. But if instead of having one linked list, where a lookup would be O of n, we now have 10 linked lists or 1,000 linked lists, now it's O of n divided by 10, or O of n divided by 1,000. And while when we're talking theoretically about complexity, we disregard constants, in the real world, these things actually matter, right? We actually will notice that this happens to run 10 times faster or 1,000 times faster, because we're distributing one long chain across 1,000 smaller chains. And so each time we have to search through one of those chains, we can ignore the 999 chains we don't care about and just search that one, which is on average going to be 1,000 times shorter. And so we still are sort of tending towards this average case of being constant time, but only because we are leveraging dividing by some huge constant factor. Let's see how this might actually look, though. So this was the hash table we had before. We declared a hash table that was capable of storing 10 strings. Well, we're not going to do that anymore. We already know the limitations of that method. Now, our hash table is going to be an array of 10 nodes. pointers to heads of linked lists. And right now it's null. Each one of those 10 pointers is null. There's nothing in our hash table right now. Now let's start to put some things into this hash table though, and let's see how this method's going to benefit us a little bit. Let's now hash Joey. We'll run the string Joey through our hash function and we return 6. Well, what do we do now? Well, now we're working with linked lists. We're not working with arrays. And when we're working with linked lists, we know we need to start dynamically allocating space and building chains. That's sort of how, those are the core elements of building a linked list. So let's dynamically allocate space for Joey, and then let's add him to the chain. So now, look what we've done. When we hash Joey, we got the hash code 6. Now the pointer at array location 6 points to the head of a linked list, and right now it's the only element of a linked list, and the node in that linked list is Joey. So if we need to look up Joey later, we just hash Joey again. We get 6 again because our hash function is deterministic, and then we start at the head of the linked list pointed to by array location 6, and we can iterate across that trying to find Joey. And if we build our hash table effectively and our hash function effectively to distribute data well, on average, each of those linked lists at every array location will be 1/10 the size of if we just had it as a single huge linked list with everything in it. If we distribute that huge linked list across 10 linked lists, each list will be 1/10 the size, and thus 10 times quicker to search through. So let's do this again. Let's now hash Ross, and let's say Ross, when we do that, the hash code we get back is 2. Well, now we dynamically allocate a new node. We put Ross in that node, and we say now array location 2, instead of pointing to null, points to the head of a linked list whose only node is Ross. And we can do this one more time. We can hash Rachel and get hash code 4. Malloc a new node, put Rachel in the node, and say array location 4 now points to the head of a linked list whose only element happens to be Rachel. Okay, but what happens if we have a collision? Let's see how we handle collisions using the separate chaining method. Let's hash Phoebe, and we get the hash code 6. In our previous example, where we were just storing the strings in the array, this was a problem. We don't want to clobber Joey, and we've already seen that we can get some clustering problems if we try and step through and probe. But what if we just kind of treat this the same way, right? It's just like adding an element to the head of a linked list. Let's just malloc space for Phoebe. We'll say Phoebe's next pointer points to the old head of the linked list, and then 6 just points to the new head of the linked list. And now, look, we've chained Phoebe in. We can now store 2 elements with hash code 6, and we didn't have any problems. That's pretty much all there is to chaining. Chaining is definitely the method that is going to be most effective for you if you are storing data in a hash table. But this combination of arrays and linked lists together to form a hash table really dramatically improves your ability to store large amounts of data and very quickly and efficiently search through that data. There's still one more data structure out there that might even be a bit better in terms of guaranteeing that our insertion, deletion, and lookup times are even faster. And we'll see that in a video on tries. I'm Doug Lloyd. This is CS50. So we've been inching closer and closer to that holy grail of data